Hey guys, hope everybody's doing okay. What we're going to do today is continue with our unit on kinetics, and we're going to talk about reaction mechanisms with a fast first step. This is a little bit different than what we looked at already with reaction mechanisms. The reaction mechanisms we looked at already had a slow first step. And since the first step was slow, that's our rate determining step, we could write our rate law from that. So the other steps were fast, but that really didn't matter because the rate determining step is based off of your slow step. In this case, the first step is going to be fast, and it's actually going to be an equilibrium system, and then the slow step is going to occur a little bit later. It's not as easy as just taking your slow step later on in the reaction mechanism and writing the rate law for that, because something would be included in that that's not allowed. So let's take a look at an example here. You guys will try one. This is pretty easy once you get the hang of it. So take a look at the following example. You have 2NO plus Br2 yields 2NOBr. The experimentally determined rate law, so we know the rate law, is going to be rate equals K times NO squared times Br2. Okay, so that's experimentally determined. We know that's what it is. It says write a reaction mechanism that is consistent with this rate law. So if the rate law looks like that, we have to write a reaction mechanism based off of that. We want to have two NO molecules and a Br2 molecule colliding. So it's really what we have in our first equation. I am just separating the two NO into NO plus NO. All right? So we get NO plus Br2 yields 2NOBr in this case. So let's go into this a little bit deeper on the next slide here. If you have your reaction mechanism based off of your rate law, first question says, why is this not an ideal mechanism? This isn't an ideal mechanism because this is a termolecular reaction. So termolecular, which is in this case third order, is very, very rare. So we talked about that earlier in a different lesson. In this case, you need two molecules of NO, a molecule of Br2 to collide with effectively, which means it needs to have the correct energy and it needs to have the correct orientation. It's very, very rare for that to occur. All right. So we're going to propose an alternate mechanism, and you're going to be given these. Okay. So don't worry about knowing exactly how to write this. Just know what it means. So the alternate mechanism is going to be as follows. You have step one, where you have NO plus Br2 yields NOBr2, and you have NOBr2 plus NO yields 2NOBr. Okay. So I know your rate law looked like it was a third order. Okay, and it looks like your mechanism had to represent that. But that's really, really rare. It's hardly ever going to occur. So our alternate mechanism is as follows. And let's see how we can take this reaction mechanism and somehow get our rate law from this. Okay, so take a look at it. Step one is fast, and we're at equilibrium. Okay, so the forward reaction is the rate of K1. Like the rate constant is K1 there for the forward reaction. And then the reverse reaction, because it is equilibrium, so the reaction is going forward and it is going in reverse. At the same time, basically, we have K sub negative 1. All right, so it's K sub 1 forward, K sub negative 1 reverse, and you can see that matches up with the half arrows, right? The half arrow going to the right is your K sub 1, and the half arrow going to the left is your K sub negative 1. For step two, that's our slow step, and it's a full step, right? It's a full going to completion step. So we just have K2. We could label that as K2 because it is step 2. So it says, what's wrong with writing the rate law for the second step, which is the slow step of this mechanism? So if we actually write it, let's take a look at writing the rate law for the slow step. You're going to have rate equals K. I'll say K2 just to make sure we know that's what it is. And we're going to have NO Br2 times NO. Right, that's my rate law for the slow step. There's two things wrong with this. The first thing that's wrong with this is that it doesn't match the experimentally determined rate law. So right here it tells you the experimentally determined rate law is K times NO squared times Br2. That's what it has to be. So if I take my slow step, it's not matching up with that. And I know what's on the screen in front of you in that box. That is my experimentally determined rate law. So I need to end up getting that somehow. The other thing that's wrong with this is that look at what you have in step 1 and step 2. You have NOBr2 canceling out here and here. What is NOBr2? NOBr2 in this case is an intermediate. So the next thing that's wrong with this is that your intermediate is in your rate law right here. And your intermediate should not be in your rate law. Okay, so that's something very important to remember here and to know. So two things wrong with this. Number one, it doesn't match up with your experimentally determined rate law, and that is the only way to determine rate law. And the second thing wrong with this is that the reaction or the rate law is including the intermediate from our reaction mechanism, which is not allowed. Okay, so those two things you should have written down for why this isn't allowed. So how do we fix this? Here's our mechanism once again. Let's rewrite the rate law for the first step. Okay, so let's go ahead and do that. I'm going to make sure I don't run out of room here. So rewriting the rate law for the first step, you have two reactions going on here, the forward and the reverse. So let's summarize that here. So we have the rate of K1. Okay, so the rate of the forward reaction is equal to the rate of K2 of your reverse reaction. Oh, I'm sorry, that should be K minus 1. Oops. Let me fix that. K minus 1. All right, so the rate of K1 is equal to the rate of K minus 1. So again, you're at equilibrium. We know what this is from many units ago. The rate of the forward and reverse reaction is equal. That's when you're at equilibrium. That's what it is. So let's substitute in the rate expression for our forward reaction and our reverse reaction into this. Okay, so what I'm going to do is the rate of the forward reaction, the rate law, is going to be K1 times NO times Br2 equal to the rate of the reverse reaction. So the reverse reaction is going backwards, going this way. All right, so that's just going to simply be K sub minus 1 times NO Br2. All right, so that's what I have. That's what I have here. So I have K1 times NO times Br2 equals K sub negative 1 times NO Br2. All right. Next step is to rearrange your rate law and solve for the intermediate. Okay, so let's go ahead and do that. Make sure I have enough room here. Let's solve for the intermediate, which is NO Br2. All right. So to solve for the intermediate, I want to divide both sides by K sub negative 1. So what I'm going to get is K sub 1 over K sub negative 1 times NO times Br2 equals concentration of NO Br2. Okay, so all I did was divide both sides by K sub negative 1, and I end up with I just grouped them together here on the left. I have my K sub 1 over K sub negative 1 times NO times Br2 equals concentration of NO Br2. The last step is to substitute the formula for the intermediate into your rate law for step 2. Okay, so we still have to write our rate law for step 2, but the intermediate's not allowed to be there. So we're substituting in the intermediate into that rate law for the second step. Okay, so let's go ahead and do that. So the rate law for step 2, if you remember, was simply rate equals NO Br2. I know you have this on your paper already, but I'm just rewriting it here because it's a different slide. Okay, so your step 2 rate law is that. Okay, rate equals NO Br2 times NO. Now let's substitute this, okay, substitute that into where it says NO Br2, okay, in your rate law up here. So let's go ahead and do that. So we have rate equals, and then instead of putting NO Br2, we're going to put K sub 1 over K sub minus 1 times NO times Br2 times NO. Okay, so this, okay, this right here is my substitution. Okay, I actually forgot to put K2 here in my rate law. So rate equals K2 times NO Br2 times NO. So that should be here as well, K2. And then it says at the end here, combine your rate constants. So like all these rate constants end up just being a constant, right? So rate equals K. I just combine them all into K. Doesn't really matter what sub whatever they are here. So rate equals K. And I'm just going to clean this up a little bit. I'm going to move my two NOs next to each other and combine them. Okay, so that is NO squared times Br2. All right, so all I did here was I still use, like you still have to go off of your slow step Okay, so I still have, I know this is getting cluttered here, I still have to write my rate law for my slow step. Okay, but your intermediate is not allowed to be in that. Okay, so what you need to do is take your fast step and then write the forward reaction equal to the reverse reaction, your rate law of forward equaling your rate law of reverse. Solve for your intermediate and substitute that in. Okay, look what we get. Here's our rate law, substituting in NO times BR2 plus my constants in for my intermediate, and you end up with the same experimentally determined rate law as you had back here. Okay, so experimentally determined rate law was K times NO squared times BR2. Looks good. Okay, guys, that's how you do this. So there's one that you're going to try here, and it says to show the following mechanism for the above equation, or below equation, also produces a rate law consistent with the experimentally determined one. So there is your reaction mechanism. This is the practice problem on the bottom of your page right here. And we want to see that, or you want to show that this reaction mechanism is also going to equal the same rate law as the problem that we just did. Okay, so this is just an alternate reaction mechanism for the first problem that we did. So go ahead and do the same process, right? So your experimentally determined rate law here is still going to be this, all right, what you have on the screen boxed in here. But this is just a different reaction mechanism trying to get to that. So go ahead and try to figure it out based on this reaction mechanism. So your first step is your fast equilibrium, your second step is your slow step, and then we will go through and solve it and see if you get the right answer. All right, give it a try. Okay, let's see if you figured it out and got the right answer here. So you're going to take a look at your slow step, and your slow step is your rate determining step. So I'm going to write my rate law for that. So I'm going to get rate equals K times N2O2 times BR2. All right, and if I take a look at that, I know that is not the correct rate law because my experimentally determined rate law is the one that you had a couple slides ago. It was the same experimentally determined rate law as the first example that we did, which was rate equals K times NO squared times BR2. The other issue here is we have an intermediate involved in my rate law, which is not allowed. Okay, so let's go ahead and figure out how to do this, and we're going to do that by using the first equation. All right, so I'm going to look at my fast equilibrium step, and I have the rate of the forward reaction equal to the rate of the reverse reaction. So I'm going to have K sub 1 times NO equals K sub negative 1 times N2O2. All right, so that's my first step, setting up my forward and reverse rates equaling each other. I'm going to solve for my intermediate, so I'll divide both sides by K sub negative 1, and what I'll end up with is K sub 1 over K sub negative 1 times NO equals N2O2. All right, so I have that there. Now I have my intermediate, which is right here, and I'm going to substitute everything I have from my intermediate into my rate law for the slow step, into where the intermediate is, because I'm not allowed to have that in the slow step. So let's go ahead and do that. So I'm going to get rate equals K times K sub 1 over K sub negative 1. And that's going to be times NO times BR2. So I can't forget that as part of it. And now I go ahead and just clean it up a little bit, and I get rate equals, combine my constants and just get K times NO squared times BR2. Okay, that takes care of it. So it looks like it all works out very nicely, and my experimentally determined rate law from a couple slides ago is going to equal my rate law right here from my slow step with my intermediate substituted into that. Okay, so this is very simple, guys. If your slow step is the first step, then just write the rate law for that slow step, that slow elementary step, and you're good to go. If your rate law is not the first step, find your fast equilibrium step, and then, of course, solve for your intermediate, plug it into your rate law for your slow step, where the intermediate is, combine it all and clean it up, and we are in good shape. All right, guys, that takes care of rate laws and reaction mechanisms with a fast first step and a slow step that comes later on. If you have any questions, let me know. That takes care of it. Thanks, guys.